Sorry about that. Hello, everyone. We're really excited to talk to you today about how how Square has been using Envoy as the basis for our service mesh. I'm Michael Puncel. I've been at Square for about 5 years. For the first 4 of those, I was working primarily on our deployment systems, the most recent one being called P2. And then for the past year, I've been on our traffic team working on exclusively this project, rolling out our Envoy service mesh.
Hi, I'm Snow. I've been working with Square for 2.5 years. Last 1.5 years on the traffic team, also working on Envoy and service mesh stuff. So for this talk, we want to talk to you about our motivation for moving to Envoy, as well as cover some of our infrastructure details to shed some context as to why we made the decisions that we made. Then we'll cover the design of our service mesh, including the control plane, how we set it up to facilitate migration to the new setup. And we'll cover security, some more traffic shaping features that we're making use of, and we'll tell you about where we're at now and what the future looks like. So one of the big things for us was that we really needed to simplify the way client and server libraries worked when it came to service traffic. Square has 3 major languages, several minor ones, and you get a lot of different languages and frameworks they have to keep up to date, and feature parity becomes a huge problem. We wanted to distribute load balancing because we've been previously using hardware load balancers that were becoming an increasing availability concern. We were having load issues, and we really needed to get rid of the bottleneck. We also wanted to really abstract away infrastructure from app developers because previously they had to know a lot about a lot of infrastructure details in order to do their job well. So we really wanted to make sure that they could just keep doing what they're good at, developing all our products. And lastly, we really wanted to make it easier for us to make larger infrastructure changes. And Envoy gives us a lot of that with both the extensibility of custom filters, as well as the centralized control plane that gives us a lot of power to move, to roll out changes really quickly. So Square runs primarily in our own data centers. So we have a few cloud expansions as well, but primarily our own data centers. This is all just bare metal. We run our own Kubernetes-like deployment system that similar in the sense that it has pods that you can run multiple things in the same pod, Kubernetes-like, but it does not use containers. It's all just multi-tenant hosts. The only isolation between multiple apps on a single host is user permissions and like some C groups. So there's no network namespacing. Then we've been using MTLS between everywhere for a while now. We have pretty strict security requirements as a famous company, so this has been a requirement previously and continues to be so with Envoy. And lastly, we're running on mostly CentOS 6. We're slowly moving towards 7, but it's a long process, so we're working on it.
Okay, now we'll get to the main part of our talk, where we'll go over a few parts of our design of our service mesh that we think are particularly interesting to talk about. So the first thing that you'll probably think about if you're rolling out a service mesh is what your control plane will look like. So we decided to go with a centralized control plane because, as Snow mentioned, that really helps you make changes very quickly, where you can deploy a single server and really change the way that all the envoys are wired together. We also went with the decision to build our own control plane. The main reason for that is because we already had a fairly sophisticated mechanism for how traffic is routed at Square. And so we felt like we really needed control over all the knobs that Envoy has in order to make things look very similar to the way they looked before, but moving on to Envoy. So our control plane looks a little something like this. We use the Java control plane library, which is the same as the Go control plane one, if you're familiar with that. It's on the Envoy Proxy GitHub. The bottom part there is the XDS server, which was discussed in the last talk. So that's basically the actual gRPC server that handles all the version acknowledgement and all that kind of stuff. Then there's a snapshot cache, which is a place where after you generate a given Envoy configuration, you save it into the cache where it can be used later. I'll walk through how exactly that works in a second. And then the final piece is what we call the snapshot factory. And so that's some code that we wrote that's very specific to the way Square works, and it generates Square-specific Envoy configuration. On the right, we have the two primary data sources that our control plane uses to generate config. We have an access management registry that knows about every microservice we deploy. It also knows which microservices talk to which others, so it knows the dependency graph. It also knows the identities of each cert that the clients will be using, so we can use that for MTLS. And then we have a service discovery database that, of course, tells us where on the network certain pods are available. It also has a lot of traffic shaping information that Snow is going to talk about later in more detail. So when an Envoy boots up, let's call it foo Envoy, so it's associated with the app foo. It'll make an XDS request as described in the last talk, where it doesn't yet have a version that it can act, so it sends an empty version. The XDS server will then look in the snapshot cache for, do I have a config that's suitable for foo? It doesn't, so it calls a callback in our code. We then pull in information from those two databases, generate an Envoy configuration for foo, save it in the snapshot cache, and then the XDS server is able to respond to that Envoy. And we think that it's potentially interesting that we're doing lazy generation of snapshots here. That's really cool because it means you don't have to pre-compute every possible permutation of Envoy configuration you might need up front. And it also means that we can pass up a ton of information in the metadata of the XDS requests. And so we can do things like toggle features on and off in the client, where you pass your Envoy some configuration when it boots, and then that will later be used in the control plane to decide which features to turn on. Then if something changes, so the Envoy re-requests for version 1, because it's last seen version 1. If something changes in our databases, our snapshot factory can go ahead and create a new snapshot configuration with a new version, and the XDS server will respond with that, and then our foo Envoy re-requests. To show you a little bit what the control plane library gets you for free, if we have a second foo Envoy startup, it's able to just look in the cache and respond. And so our snapshot factory didn't even get invoked, didn't have to do anything. So it's very low overhead if you have a lot of the same configurations being served over and over. And then when we get an Envoy with a different identity bar, we could kind of go through that original flow where you generate a bar configuration. Oops. Oh, and then when the foo envoys drop off the network and stop requesting, eventually a garbage collection routine in the Java control plane goes and clears out that entry in the cache. So that, again, helps you not have to think about what kinds of configs you need at a given moment. You can just generate whatever on demand for whatever requests come in, and then eventually they'll get cleaned up if they stop being used.
All right, so in addition to the control plane itself, we felt that we needed to do some additional work to make it safer to roll out changes to the control plane. So previously we were discovering the control plane itself just using DNS and like randomly picking a host to connect to, which meant that when we deployed a new version, in this case a bad version, for all we know, these envoys might, when they restart, randomly both connect to the bad control plane, and they both crash or like whatever happens with the bad deploy. So we felt that this was ended up being pretty risky whenever we rolled out new changes, especially changes that could not easily be controlled within the app, such as high-level configuration changes. So we decided to put a proxy in front of it, because might as well put more proxies in the system. And what this allows us to do is that when you do a deploy, with the same bad control plane, the proxy consults a feature flag service, that it uses that alongside the metadata in the request that's sent up, which identifies the envoy, so which app it runs next to, all this stuff. And using that alongside with the rollout values in the feature flag service, it can decide which control plane it connects to. So when it does that, we've now limited the impact of this bad envoy to only this one envoy that was connecting to the bad control plane. And once we see this is bad, we can flip it back just on modifying the feature flag, and we can roll back the bad, deploy a good version, and then slowly move that over. So this is really cool because it gives us essentially green-blue deploys of the control plane. And while we're still in the process of rolling this out, it has given us a lot more confidence in making bigger changes to the control plane and ensuring that doesn't take down the entire company.
Another piece of rolling out a service mesh is actually migrating. And this kind of ends up being the most time-intensive part. It's kind of harder than the engineering pieces. So at Square, we have about 500 different microservices that are deployed, and we were 3 ICs working on this. So it was really key that it's as easy as we can possibly make it to migrate a service. So the first thing that developers do when they want to add Envoy to their service is they run a command we give them called traffic CLI add Envoy. And that does basically all the infrastructure things that need to go into it. It's going to be different for everyone. But the main thing it does is actually deploy Envoy into your pod. There's like ports that open. Things get registered in various databases. Just everything that you need to do to get it deployed. We also provide client and server libraries in all the major languages that in use at Square. And actually, the server libraries kind of just talk to the deployment system and enable the listener to get traffic in from Envoy when you do your deploy. So that traffic CLI add Envoy step is all you have to do to then be ready to receive traffic ingress through your Envoy, which is pretty cool. It takes like 5 minutes for someone to do. Another thing that we tried to do is keep the clients as simple as possible. So basically just push as much stuff out into the proxy as you can, because that's going to make it much easier for someone to write a client library if they want to start using a new language that you haven't been using before. And so the way it works is basically you send all your requests to a Unix socket. I'll talk about why we're using Unix sockets later. And you format your host headers for your HTTP requests as production or staging, the name of the server app you want to talk to, .square. And so that's basically exactly the information that developers know when they're developing an integration. They don't want to know anything about load balancer host names or IP addresses or whether they're on the cloud or on premises. They know what they're trying to talk to. And another thing that makes migration possible for us is preserving the way that our existing service discovery and traffic shaping stuff works. And we're going to talk about that in detail later. But you're going to live in a world where you're halfway on Envoy and halfway not. And if things are really operating very differently, that's going to be a challenge. And then we also have a feature flag that we call the VIP to mesh feature flag. To show you what that does, suppose we have a ring of 3 microservices that all have a circular dependency on each other, Mo, Larry, and Curly. They talk to each other through a VIP, which is a virtual IP that's sitting on a hardware load balancer somewhere. And let's say that Mo's team finally has some time to do their Envoy migration. So they do traffic CLI add Envoy. They have Envoy deployed in their pod. But we haven't done anything yet to actually change the flow of traffic. So it's still going from Mo's VIP into the app, and the app is still talking to Curly's VIP. So the naive thing to do here would then be to have them flip their client configuration to start using the mesh. But there's no Envoy on Curly's side yet because they haven't gotten around to it. So what we ended up doing is we have our control plane. By default, your Envoy will send traffic to that old VIP that we know is working because we're already using it. And then later on, when Curly's team gets around to deploying their Envoy, they can flip a feature flag that says, hey, I'm ready to take traffic ingress through my Envoy. And then our control plane will tell all the clients to go through that. So this is really nice because it means that Mo's team can finish their Envoy migration where they deploy their Envoy, they flip all their client configuration, and then they're done as far as they're concerned. They can go back to writing their products. And Curly's team later on at some point will flip a flag that actually turns on the full mesh. And then when you continue this, you eventually get rid of all the VIPs and have a full service mesh, which is what we're trying to get to. One more thing that's pretty important if you're using Envoy is, and you're using TLS internally, is being able to offload that into the proxy. So you want to be able to take advantage of all the layer 7 features that Envoy has, like tracing and metrics and request level load balancing. And it's also nice to be able to enforce TLS in the proxy layer, so you're not depending on client, like app configuration to do it. And for us, as Snow mentioned earlier, we're not using containers with network namespaces yet. So that's why we're using Unix sockets for egress traffic. So the app is talking unencrypted HTTP to the proxy into a Unix socket that's protected with file system permissions. And so that lets us kind of get the behavior of having a private network on loopback without actually being able to do that yet. And then we are still having apps, server apps enforce layer 7 access control. So if you want /foo to be allowed for a certain client but not /bar, The apps still have to enforce that. That's something we want to do later, but we facilitate that with having Envoy pass client cert details in a HTTP header on every request.
All right, so now I want to talk about some of the traffic shaping and routing features that we use. And most of these, well, all of these have been in order to somehow replicate the existing RPC framework that we had. Again, because as Mike said, we want to make sure that people could live in this transitionary world without having to know who's calling you, so that make everything look the same. So first, I just want to go quickly over what the service discovery model has looked like at Square. Where you have the app, which is the routable target, and then you have each app contains multiple deployments, corresponds to a cluster of pods. So when you target an app, you'll hit one of their deployments, and deployments can be the same or they can be slightly different configuration. Maybe they're running a different version, but they're all collectively running the same app. Additionally, each deployment exists within the data center, which just describes their physical location in the world. And so with this, it was important for us to ensure that traffic always prefers the closest possible data center. So in the case where you have Envoy running in one data center targeting two different deployments, this is one app, two different deployments, one in the same data center, one in a different data center, you want to prefer sending traffic to the first one and then start failing over to the other one only as the second one becomes available. The first one becomes unavailable. So to do this, we simply just use Envoy's priorities. The control plane will generate based on where the client is, will generate the priorities by looking at a pre-ordered list of data centers so that we know, prioritize them in order of proximity. Additionally, we allow app users to kind of mess with this concept by introducing what we refer to as virtual data centers, which is the ability for them to put two data centers into the same data center so that they can say, oh, treat these two as if they're in the same data center, which essentially puts them, gives them the priority of the closest data center. This becomes really useful when you use it alongside locality weighting, which is what we use in order to allow app owners to assign weights to individual deployments. And this instructs Envoy to load balance accordingly. In this case, deployment B gets more traffic than deployment A, and giving app owners the ability to flip these changes as they please becomes really powerful because that gives them a lot of flexibility. They can do green, blue deploys. They can do gradual failovers between data centers by utilizing virtual data centers alongside this. Essentially, you have two data centers, you put them in a virtual data center, and now you can just control the traffic between the two of them. So you can do, instead of doing a binary switch, you can slowly bleed the traffic over. So as mentioned, the deployments have slightly different configurations. So there are use cases in which apps want to target a specific one. So to do this, we associate metadata with each of the deployments and use the subset load balancer. These essentially are labels that we allow people to put on the deployments whenever at runtime, and they'll be updated in real time, which allows a client to specify where they want traffic to go. Well, instead of setting a header, in this case, you want to target the master label. So just specifying that will ensure that all your traffic only hits deployments with the specified label. So similarly, you can hit the v2 label, which will now hit both of them. And being able to move these labels around at runtime makes them really powerful and flexible when it comes to failing over not just traffic, but also stuff like which is the master side, who's responsible for writing to the database in an active system. So you can use this both the clients calling the app, and internally you can proxy. All of these use the same labels, so you can you get a lot of flexibility from this. And so the last traffic bit I want to talk about is retries. So for Square, every request, a lot of our requests are very important because it's payments, and if one request fails, somebody's not getting paid. So in a lot of cases, we really want to make sure that requests succeed. So we make use of not only the Envoy automatic retries, but also a bunch of smart retries. So the idea being that when you retry a request, you want to make use of the information from previous attempts to improve your chances. So the most interesting one is the Cross-Datacenter Retries, which is the idea that there are cases where you have an active-active setup where in multiple data centers you have all your resources somewhat duplicated. You have two clusters of databases, a sharded database in one each data center. And since it's a sharded resource, you might be partially down in the closest data center. So if one shard is down, you're still able to serve traffic. 90% of traffic is succeeding, so you don't want to go unhealthy. But 10% of traffic is consistently failing because the shard is down. So it happens so that in the other data center, the entire resource is available. But with Envoy by default, when you target just by priorities, you will never drift down to the second priority unless the first priority is unavailable or unhealthy in some way. So we configure Envoy to use send the first few retries to the closer priority, and if both of those fail, it will adjust the priority table and send the next few requests to the second data center. And this is very important for a lot of our highly available active-active setups because they've been relying on this behavior in our existing system. So instead of putting this logic in the app, you have it in the RPC layer, so you get this kind of nice automatic failover between data centers when retries are happening. And to run this in Envoy, you just use this retry plugin that we upstreamed. So you can just use it, just configure it. It's easy.
So to talk a bit about where we are now with our migration, we have feature parity with our old system. So all the same traffic shaping, retry behavior, service discovery things. We have Envoy currently partially rolled out. There are somewhere like around 120 or 140 different microservices that are using Envoy, 2,000 sidecars total. I think we'll get pretty close to 10,000 when we're done. And we're using Envoy both on premises and in the cloud. Very limited in the cloud, but we are already seeing that benefit of being able to abstract the platform that the app is running on and just talk to the thing that I want to talk to. So what's next for us? Of course, we're going to finish this migration, get rid of those hardware load balancers, all that good stuff. In 2019, we're also going to look into migrating to Kubernetes. So we're interested in chatting with people this week to get people's wisdom on that. We're excited to try out Spiffy integration, particularly using Envoy's Secrets Discovery Service API, which lets you do cert rotation on a really regular basis without having to do any restarts of processes. We also want to push layer 7 access control out of our server applications and into Envoy itself. And then we're going to look into also replacing our edge and forward proxies with Envoy so that we can just have one proxy to be familiar with. That's all we have today. I have our email addresses and Twitter handles on there if anyone wants to ask us questions afterwards. I think looks like we might have a few minutes for... So we have 3 minutes for questions if anyone has any. Yep.
So when you say you run Envoy, right, you run Envoy as a process or as a container, seen any difference between?
The question was, are we running Envoy as a container or as a normal process? Right now, we're using it as a normal process. For a little bit, we were trying it with Docker, but for unrelated reasons, we decided to roll that back. We have not done any horse racing or anything like that comparing the two, but it works totally fine as a normal process. Yep.
How is high availability handled for control plane that you're running?
You want to take that one?
Yeah, so...
Just repeat the question.
Oh, yeah. The question was, how is high availability ensured for the control plane? So first off, it's somewhat by design, the entire system is resilient to the control plane going down. Like the control plane being unavailable simply means that config changes are no longer being propagated, which is fine for a little bit. It just means, in our case, it means that if hosts are moved around, they won't be updated immediately. If a deploy of a new thing goes out, it's not going to get propagated out. So short failure, like a temporary failure of the control plane is not that bad. That said, we do run it multiple instances, so we have maybe 6 or 7 instances running, so if an individual host goes down, this is all just, again, with the proxy is aware of all of the backend hosts and will load balance between them. So, and just retry into a different one if one is unavailable.
And then there's also caching in the control plane itself of, so if the primary data sources like service discovery or access database go away, you'll be able to run on those old configs for a while. So as long as your service topology isn't moving too much, you'll be okay for a little bit. We haven't really seen a problem with that. I mean, it's things kind of are coming and going at a slow rate. The question was, do we see problems with control planes not being in sync? But in practice, processes are not moving around so frequently that that's a problem if you do a little time traveling. We haven't really seen a problem with that. Do we have any, how much time do we have? Okay. All right, yeah.
You mentioned that you kept your clients simple. Do you provide the header features? Like, how do you handle passing your retry, custom retry policies and circuit breakers?
The question was about keeping our clients simple. How does that work? So for now, we've been using clients that have very heavy YAML configuration for a long time, and we use monorepos pretty extensively. So it was pretty easy for us to just change the config structure, and then people just rewrite their YAML config, and then now they're using our Envoy client we wrote. For retry behavior, we use protobufs almost everywhere, and we have special annotations that dictate what the per try timeout should be. Clients decide the overall timeout themselves, and we're not using circuit breaking or anything like that yet because we've not wanted to surprise anyone with all of a sudden requests are failing and it's Envoy's fault. That's something that we want to do at some point, but for now we just set everything to 10,000.
Another thing we did that was nice with the clients was that we basically edited existing HTTP clients, which already had retry and timeout features. So we just converted that config to just set the right headers so that instead of having the client have to enforce it, now Envoy is doing it.
Yeah, in the back. The question was, are we using Envoy in front of our databases? We're not yet. That's something we might do at some point because it could make the database failover mechanisms simpler potentially, but we're not doing it yet. Yep.
How do you monitor Envoy? And how do you distinguish between application failures and proxy failures?
So most of the monitoring is being handled by app owners themselves because they are the ones who are running it next to their process. And this is still something that we're working on. It's kind of tricky because people are not used to seeing HTTP response code when they're timing out. For now, we've just been teaching people to look at the access logs, which will tell them whether it's a response code generated by Envoy or whether it came from the upstream. But I think it's something we're looking into, exposing this in exception messages in the client code, that kind of stuff. But we're not there yet.
I think that's all we have time for. Thank you so much for listening.